Good morning, everyone, and welcome. Here is our outline for today, which will include all 5 stages of my study, as well as questions and answers at the end. A special welcome to my dissertation committee, including Chairperson Dr. Vince Nix and Drs. Kelly Brown and Dr. Hunter Keeney. My deepest thanks to each of you. As you know, I'm Keith Reeves, so without further ado, we will begin with the essentials. There is an identified gap in the literature regarding the design of standards-based report cards, or SBRCs, which use different arrangements of performance level descriptors, or PLDs. Their design is often arbitrary, leading to teachers and schools making educated guesses at best and harmful decisions at worst. By identifying which SBRC models are most effective, if any, and which are better or worse for students, we can make better design decisions. Existing research shows that the more that we label, categorize, and judge children, the more psychological and socio-emotional harm they suffer. Because some SBRC designs use many more PLDs than others, we must investigate. If a particular model more accurately predicts outcomes than others, we should use that model. If no particular model is better than another, we should use the fewest possible number of performance levels to better safeguard child health. Consequently, the purpose of this dissertation is to examine the relationship between SBRC models with different PLD permutations and the end-of-course standards of learning tests, which are considered in Virginia to be valid indicators of the mastery of the standards. The theoretical framework within which this study exists is as follows. Maslow's hierarchy of needs held that the more children's basic needs are met, like safety and security, the more likely and easily they can satisfy higher level needs. Constructivist psychologists Piaget and Vygotsky held that children's learning experiences are inextricable from their human development. Paulo Freire's pedagogy of the oppressed held that teaching and learning must necessarily lead to positive social change. This deeply influenced Joe Kinchlow's critical constructivism, which held that social context shapes and influences the way we perceive ourselves, others, and that world. Benjamin Bloom's mastery learning discarded traditional learning structures that failed to meet student needs in favor of simple descriptors alongside meaningful feedback for learning rather than after it. Cohn and Miller are 2 important scholars that indicted poisonous pedagogies, as Miller put it, that are directly harmful to children, like ranking, categorizing, and judging. Tom Guskey, in works spanning 1994 until the present day, along with his contemporaries, have consistently shown that standards-based grading is far healthier for kids and better for learning than traditional grading. That brings us to this study, bringing the entire theoretical apparatus to bear on identifying which specific forms of standards-based praxis are most effective for teaching and learning and least harmful to children. The dissertation asks 3 research questions. Is there a relationship between qualitative standards-based report card models and students' quantitative standardized test scores? Do different SBRC models offer different varying levels of predictability, and are certain SBRC models preferable? Limitations being phenomena beyond the researcher's control for this study included the pandemic, the timing of data collection, and a failure of some schools to provide equity-related data, which I'll mention later. Delimitations being restrictions that the researcher places on himself, I delimited the study to only SBRC models for which I could acquire sufficient data saturation. I also delimited out of the study 1 entire school division's data because they retrofit their SBRCs to use traditional letter grades, which is anathema to SBG in my opinion, as I'll explain. Stage 1 was conducted over the past 2 years as a systematic literature review. I read, analyzed, and codified approximately 208 academic sources during this stage, along with numerous other supporting pieces of evidence, literature, journalism, and commentary. Those sources span 109 years back to 1912. I've arranged this literature review chronologically to paint a picture for our committee and the audience of the history of grading in America's schools, and then I will review the major themes that emerge. America's first public school was founded in Boston in 1635. From this founding until the latter half of the 18th century, grading and ranking of students was quite rare. The earliest known American system of grading emerged in a 4-level system at Yale University in 1785, which used 4 Latin phrases that roughly translate to best, second best, inferior, and worst. By 1813, Yale had begun to use a four-number system in lieu of the Latin PLDs, which is believed to be the progenitor of today's 4.0 GPA system. Note, 178 years passed, during which we showed King George a little something, and now, only now, introduced number grades. Traditional grades have not always been a part of school. And good morning, Dr. Keeney. By 1837, Harvard University had adopted what's thought to be the first instance of the 100-point numerical scale. In primary and secondary education prior to this mid-19th century, over 2 centuries of American education, if we're looking at the timeline, report cards were very uncommon. Instead, teachers communicated with students and families verbally or in narrative form, but either way, directly. Also of note is that in the era before industrialization, students were generally grouped together based on local geography. Sorting students into grade levels by age was, again, relatively uncommon. During industrialization, this flipped. Time elapsed instead of level of achievement became the primary arbiter of advancement. As industrial thinking became the dominant force in social institutions, numerical scores became increasingly prevalent in primary and secondary education, rising especially in the 1910s. Like factory commodities or eggs, children were graded with letters as schools became mechanism for sorting students into intellectuals as potential experts, workers as potential laborers, and what we might call undesirables, or other permutations thereof. In the aftermath of World War II, it became evident that these sorting mechanisms had created significant divides in our national fabric. The social justice era of the 1960s saw schools shift further into the business of controlling students, and as such, conflated skill mastery with compliance. These non-academic factors, like appearance or tardiness, collectively termed deportment grades, got folded in to traditional grading. The 1965 Elementary and Secondary Education Act created many new national requirements and began the era of standardized testing and accountability. Throughout the 20th century, critics raised concerns time and time again about the invalidity of traditional grading. In fact, Marzano stated categorically in the year 2000 that there is no, not a little, but no evidence to support their use. As part of this new outcomes-based movement that later became known as the standards-based movement, Bloom created mastery grading in 1971. The infamous 1983 A Nation at Risk report released during the Reagan administration sent a shockwave through educational policy, and 2 basic camps emerged. The industrial neoliberal camp that believed in privatization and free markets as a solution for all things, and the standards-based camp that thought to eliminate institutional industrial thinking from schools. Unfortunately, standards-based reform was seized upon by that very industrial neoliberal camp as a chance to institute standardized testing reform, leading to the testing-centric era of No Child Left Behind in 2001, and the subsequent back-and-forth battles we've seen over the last 20 years between industrial neoliberal testmongers and pro-child standards-based reformers. The major themes that emerge from all this are as follows. Prior to the mid-19th century, education in America was mostly devoid of ranking and grading, with local communities of varied aged children learning together and receiving feedback from teachers in narrative form. Experiments arose during the rise of industrialization and eventually led into age-based grouping, number and letter grades, and by the 60s, the rise of standardized testing. We can divide our history, therefore, into the pre-industrial and the industrial neoliberal, the latter of which has been consistently critiqued as including assessment practices that are deleterious to learning. We can better investigate why standards-based grading is superior to traditional grading by understanding the 2 basic forms of assessment, norm-referenced and criterion-referenced. The purpose of norm-referenced grading, like traditional grades, is to rank subjects relative to each other, then classify them into performance groups. Criterion-referenced grading, by contrast, like standards-based grading, doesn't compare students to each other, but compares a student's performance to an objective standard. It removes the normalizing, often curve-based phenomenon endemic to norm-referenced grading. Norm-referenced grading has been shown since at least 1912 through a series of landmark studies by Starch and Elliott to be inaccurate, arbitrary, and ineffective at communicating skill mastery. It assumes that all student performance will always be on a bell curve, an inappropriate assumption to say the least, and it perverts objectivity by including those deportment grades we discussed, like tidiness or lateness. Students and families across demographics tend to regard A as good and everything other than A as bad. C doesn't mean average in actual practice. It means bad. Numeric scores often don't honestly describe the human circumstances of children. Punishing a child who is absent during a test for, say, a death in the family is not an honest assessment of skill mastery. When mathematics cannot account for the human, the system has failed. Such systems have been shown to be especially biased against girls and people of color and to be harmful to student learning across all demographics. So here's a practical example of this. This student begins with a 60, whatever that means, in week 5. The student is slow to develop mastery, but by week 9 has achieved an 85. The next student begins and ends with precisely the same score, but has a more linear trajectory in their unique learning experience over 5 weeks. Then this final student has an early epiphany, then plateaus at the final mastery level. If we remove the process of learning and only look at the outcome, the students end with the same level of achievement, but certain learning journeys have been punished because of the math itself. This is even more obvious when that traditional conversion from number to letter grades is applied. These are the 3 students with the same outcomes, and yet they are classified and therefore judged differently. Research from a massive body of literature from more than a dozen scholars spanning 30 years has consistently shown that standards-based practices provide clearer, more informative, more effective communication of skill mastery for students and families, and are effectively devoid of the bias and endogenous validity errors of traditional grading, and have improved student outcomes and parent understandings. Within standards-based grading, this review identified different arrangements of standards-based report cards, or SBRCs as you'll hear me call them repeatedly, ranging from anywhere between 2 and 6 PLDs. What is not clear, the knowledge gap, is how many PLDs are best, how those PLDs should be arranged, and what those PLDs should be. Shockingly, nobody appears to have ever researched this. Well, that's where I come in. This deficit is addressed through 3 more stages. According to Cresswell, 2003, and Tashikori and Tedley, 2008, the type of study this dissertation employs is both rare and complex. Of course it is, I heard you all just say, friends and family. Because it's complex, let's diagram it. This study is mixed methods because it uses both qualitative and quantitative methodology. It does this one stage after another, not simultaneously, making it sequential. This study is exploratory and transformative because it begins with qualitative, interfaces with and transforms the prior stages into quantitative, then returns to qualitative. There are 5 stages in this sequential, exploratory, transformative mixed methods design. Stage 1, which you've seen, was that systemic literature review that we just did. Because there was no existing way to classify standards-based report cards, stage 2 required me to develop a new system. Stage 3 then applied this new taxonomy to SBRCs found both in the literature and in observed use here in Virginia. Stage 4 is the interface point and transforms the results of the taxonomy into a quantitative analysis. The dissertation concludes with concrete recommendations for on-the-ground educators, which Cresswell identified in 2012 as a hallmark of effective mixed methods designs. Additionally, Harrison, Riley, and Cresswell in 2020 established 6 new criteria for methodological rigor within mixed methods research at 3 levels, high, medium, and low. And this study conforms to all 6 high standards for rigor, which I document in the written dissertation. The population for this study is the set of 15 school divisions in the Commonwealth of Virginia that use standards-based grading for primary age students in grades 3, 4, and 5. In total, the sample for this study included 31,091 students in 45 schools across Virginia, representing a total of 82,135 individual cases that survived delimitation and data scrubbing for both validity and cleanliness. While an approximation, the sample appears to be roughly representative of the ethnic composition of the population. Sex and socioeconomic data were, unfortunately and heartbreaking to me, not available. These are critical areas worthy of study, and from an equity perspective, which I take very seriously, I encourage future researchers to investigate these potentially confounding variables. We owe it to ourselves to thoroughly investigate that. Data was cleaned into 5 primary headers. The outcome variable, the dependent variable, is the SOL score, which has a continuous interval level ranging from a minimal theoretical 0 and observed minimum of 181 to a maximum of 600, all whole integers. Several nested predictor variables for each case, the independent variables, included subject, grade level, SBRC class, which I'll explain, and the actual PLD received. For the quantitative stage 4, Goss-Sampson in 2020 provided this excellent illustration that I adapted as to how to select the appropriate test. Since the dependent outcome variable of SOL is a continuous interval level, and there are several predictor independent variables, a form of multiple regression is prescribed. Now, I think it makes more sense for me to explain regression to you right before I show you the results, so let's stick a pin in that and we'll come back to it during stage 4. On to stage 2. When deciding on how to create this new SBRC classification system that I said I needed, Bailey, 1994, and Hedden, 2016, were essential. Their reading challenged me to identify whether my classification system would be a typology or a taxonomy. Because the majority of the criteria defining the two were, for my purposes, taxonomic, I opted to create a taxonomy that was empirical, based on objective examination and evidence. And while it requires a degree of manual classification that I'll show you, it is both highly generalizable and highly discriminating between classes, so I term it a taxonomy. Bailey and Hedden went on to describe 3 basic steps in developing a taxonomy. Look at all of the subjects and identify the measurable, or what he called M variables, what Bailey called M variables. Conceptualize the big ideas that emerge, and then identify the relationships between classes. Bailey specified 2 absolute must-haves for any good taxonomy. It must be exhaustive in that every potential subject must have a class, and every subject must fit into one and only one class, making it mutually exclusive. This taxonomy, as I'll show you, accomplishes both of those things. So, following Bailey, I identified 4 M variables: the total number of PLDs, the number of PLDs describing meeting the standard, the number of PLDs describing does not meet the standard, and the highest possible PLD within the model. From the M variables, we can conceive several big ideas. Each SBRC model is distinct with its own set of PLDs, and each PLD is discrete and ordinal in that they proceed in a linear progression from low to high, and it has no overlap. And as any given SBRC model has these different permutations, by identifying the M variables, those differences are accounted for. So now we define these M variables precisely, and a lot of this has been theoretical, but let me show you what it really means. The first M variable is the total number of PLDs in the model. We're going to call this T for total, and I find the best way to explain this is to visualize it. Here's an example standards-based report card model. It has 3 PLDs: approaching, meets, and exceeds. This model's M variable of T, the total, therefore equals 3. Here's a different model that uses different language and a different arrangement. However, the T value is again 3. All we're doing is counting PLDs. Now notice how I've arranged these on your screen. I've lined up that meets standard level. Keep that in mind. And to help remember, I've shaded meets and anything above it green and anything below it red. If we take the language out of it completely, just kind of using these as box placeholders, we can see 2 big domains. Anything that it is at least meets standard on the top, and anything that does not meet on the bottom. These 2 models are clearly different in some ways, but both have a T of 3. So let's make room for some more models. I'm going to scoot this down to the end here and fill in a bunch of other permutations, with each stack representing a different SBRC model. For each model stack, all we do is count the PLDs to get T, and I've labeled T on your screen here. Each stack's T is displayed at the top. The next M variable that we need to worry about is the number of PLDs in each of these 2 big domains: the number of PLDs on the top and the number of PLDs on the bottom for each model. These 2 new M variables need to be identified just like the total is T. These two domains are different levels, so we're going to call them L for level. Therefore, our next two M variables are LM for meets and LD for the level of does not meet. Notice what I'm doing. Here is the variable name on our graphic. We've got LM on the top and LD on the bottom. Let's remove these dotted lines, and I'm going to scoot this over to make room for our next concept. Remember, we go from these M variables to concepts. Instead of thinking of two boxes around each set, we instead think about one line dividing the two L's. This is the line of demarcation. It divides LM from LD, and again, you can tell this with the color shading as well. PLDs above the line of demarcation describe meets, and PLDs below the line describe does not meet. Now it's time to look at these specific PLDs to get our final M variable. Let's start by removing everything but this first PLD above the line of demarcation for each model. Each PLD literally describes a performance level. But in a taxonomy, we want clear labels for each level, no matter the language. Whether it's meets standard or acceptable or proficient or passes, all of that describes the same thing. The first performance level, or PL, that is above the line of demarcation. Each PL at this first level above the line is PL plus 1, the first positive level. The opposite is true below the line of demarcation, and I just use the same logic and call that PL negative 1. Positive PLs in LM above the line and negative PLs in LD below. We label each PL in each model accordingly, shown here. Each level above plus 1 gets another number, plus 2, plus 3, and so on, and each level below negative 1 is negative 2, negative 3, and so on. We have now given a specific label to each performance level in each model in the taxonomy. I'll add the label for each row here on the left to make it easy to see. If you'll look closely, you see that no two models are the same. Each one has a distinct arrangement of positive and negative PLs, which means a different count of LM and of LD for each model. We can now represent each model with a formula. This model has two PLDs, so think back, T equals 2. It has one PL above the line, so LM equals 1, and one PL below the line, so LD equals 1. As a check, notice that LM and LD always add up to T. Even when a model has the same T as another model, it never has the same formula of LM and LD. This T equals 3 model has LM equals 1, LD equals 2, while this one has LM equals 2 and LD equals 1. Each model has its own formula, so each SBRC only fits one formula, making the taxonomy mutually exclusive. And since the taxonomy accounts for every SBRC in the literature, it's also exhaustive. But formulas aren't convenient, so like any good classification system, let's name each class. There are two classes in this taxonomy that have a unique T value, so we'll simply name them after their T. T equals 6 becomes class 6, then T equals 2 becomes class 2. I used Roman numerals to make sure that class names aren't confused for M variables. I thought that would be useful for future researchers. That method isn't going to work for the rest of these, though, because in each remaining case, there are other models that share the same T, like those first two T equals 3 models that we looked at. We're going to need to use a different convention. That convention is called the supremum. In mathematics, the highest possible value in an ordered set is the supremum, ordered SUP or sup. Well, I suppose you could also say sup. Therefore, our final M variable to satisfy Bailey is the highest positive valued PL in each class, the sup PL. I've now labeled the supremum in each class. 3 of the remaining classes in the taxonomy have a supremum of PL plus 1, which makes them unique. When a class has a unique attribute, it's a great basis for a name. We call these the M-designated models with a lowercase m. Why? Because PL plus 1 generally describes the meets the standard, the first level above the line of demarcation. Because meets is such common language for this level, as I saw in the literature, we'll use the first letter of meets as our designation. As we did with 2 and 6, we'll start with T, but then we'll add the designation lowercase m. That makes these 3 classes 5m, 4m, and 3m. The next set of models have a sup PL of PL plus 2. These are now also unique in the remaining classes. A sup PL of PL plus 2 means the highest level is above meets. And the most common language for these PLDs, as those of you who use standards-based assessment know, is usually exceeds. So we'll use E. That gives us classes 5E, 4E, and 3E. We're moving right along here. Of the remaining models, the next sup PL is PL plus 3. These levels exceed the exceeds. This high-level descriptor isn't very common, so I selected the designation X for 2 reasons. Firstly, it's the next letter in exceeds, but secondly, historically, things that are experimental are often labeled with an X. Using the same method as before, we append the X designation to the T value to give us classes 5X and 4X. Only one model left. This unique model only has LD equals 1, but has LM equals 4. Quite unusual. Instead of using the next letter in exceeds, I used the next letter in the alphabet, which is also another letter commonly used for experimental platforms. We use the Y designation as we did before, add it to the T value, and we get class 5Y. With an exhaustive, mutually exclusive set of PLD permutations, each forming a distinct class, with established M variables of T for the total, LM and LD respectively counting the number of meets and does not meet PLDs above and below the line of demarcation, and with names for each class, the Reeves taxonomy of standards-based report card models, and therefore stage 2 of our study, is complete. We now apply that taxonomy to examples from the literature, both to confirm its function in practice and to prepare for stage 4 quantitative analysis. I applied the process shown here to every SBRC model that I found in the literature, yeah, like all of them, and in use in schools, and the taxonomy performed as desired. To classify each SBRC, we first identify T, identify the line of demarcation, and then label positive PLs above and negative PLs below. This yields a count of LM and LD. We confirm that those values sum up to T, and then we identify the formulaic representation and classify the model. Now again, saying all that out loud is one thing. Let's take a look at it in actual practice. It makes it easier to understand. This model from Georgia uses does not meet, meets, and exceeds, which is a really common and simple example. Counting the PLDs, T obviously equals 3. The line of demarcation now needs to be conceptually established directly below the first level that describes meeting the standard. This might involve identifying the language, or in some odd cases, one might need to examine rubrics or practices. And think back, this is why I said the taxonomy involves an element of manual classification instead of a wholly automated process. In this case, the language is the qualitative indicator that lets us clearly place the line of demarcation. Obviously here it says meets and does not meet. That yields 2 levels of meets and 1 level of does not meet. So we label each PL accordingly. This yields a sup PL of PL plus 2, that top level. And then we do the same, go down with the negative PL values below the line. Now all the PLDs are labeled with their PL values. This model has LM equals 2, LD equals 1. We confirm that 2 plus 1 equals 3, the value of T, and I can't tell you how glad I am that the math at this point is this simple, unlike the quantitative analysis. And now on to the taxonomy. We look for that unique arrangement of LM equals 2, LD equals 1, T equals 3. Because all classes are initially named after T, it's kind of easy. We look at versions of class 3 to find this proper classification. We locate LM equals 2, LD equals 1 here, class 3E. The Georgia model is a class 3E SBRC model in Reeves taxonomy. Here's another example proposed by the authors of Understanding by Design, which my teacher friends may know. First, we count the PLDs. Again, same process, just a different model. T equals 5. Now we conceive the line of demarcation. Now, while good is desirable, adequate is the PLD that describes enough or sufficient. which we can reasonably interpret to describe meeting the standard. Remember, we're trying to undo some judgment here. Adequate is good enough. Now, if you examine McTighe-Wiggins' model in practice, that reinforces this determination. It's not just arbitrary. If you read McTighe-Wiggins, that is what they intended in their model proposal, which is that manual classification method. This allows us to label the PL levels now. Above the line of demarcation, starting with PL plus 1, all the way up to PL plus 4, and below the line all the way down to PL negative 1. This yields LM equals 4, LD equals 1. 4 plus 1 equals 5, which is the t-value, confirming the formula is correct. And again, to the taxonomy. LM equals 4, LD equals 1, T equals 5 is obviously a form of class 5, and specifically we find it here, making the McTighe-Wiggins 2005 model class 5Y. That's how we use the taxonomy. The Reeves taxonomy, as mentioned earlier, accounts for all of the SBRCs observed in the literature and all of the theoretical permutations within the bounds of those observations. In fact, only 9 of the 11 models appear to be in either actual or proposed use. I did not identify any uses of class 5M or of class 4X. And for this study, of the 45 Virginia schools in the sample population, 3 classes are represented, classes 2, 3M, and 4E. Therefore, the quantitative analysis of this dissertation compares these 3 models. Now, we test them. As promised, let's talk about regression. Regression, for our guests, is a set of statistical processes used to examine relationships between variables and is often used to examine predictability. The word regression comes from the ideas of going back to the means that emerge when we're looking at data sets. Because our SOL score dependent variable is continuous, a linear regression is prescribed, where we look at lines across data points. Because there's more than one independent variable, as I said earlier, it's a multiple regression. But specifically because those variables are nested or interrelated, then we need to look at them in order, which forms a hierarchy. When we perform a hierarchical linear regression, we can run tests to account for similarities between cases, such as when students have the same grade level. This is called a fixed effect. We can also run tests to account for differences between them, such as when students get different PLDs. This is called a random effect. The test performed in this dissertation's quantitative analysis accounts for both, which is why we call it a mixed model test. Hence, the quantitative methodology employed in this stage was a hierarchical mixed model linear regression. Regressions give us several important outputs, and the most commonly referenced output is the p-value, which tells us if there's a relationship between variables. However, Wasserstein, Hyatt, both 2019, and their contemporaries provide recent critical counsel that we must not overinflate the importance of the p-value. Instead, the ASA, as I've put on your screen, advises us to examine and report the size of the effect if an effect is found. In short, if a relationship is found that is statistically significant, but it has no practical effect, then it's not practically significant. Now, the minimum threshold for the bare minimum of practical significance, according to Ferguson 2016, is a Cohen's d test of 0.41. And you're going to see me highlight some stuff that comes back to 0.41 in just a moment. Using the Minitab and SPSS statistics programs, I used 2 analysis sub-questions, which I've put on your screen, to answer the first 2 research questions. And I'd like to present them to you sequentially and explain my interpretations. This visualization illustrates that the outcome-dependent variable that I investigated, that SOL test score, is parametric or normally distributed. For guests, basically that means it's on a normal curve, which you can see on the screen. As I said earlier, not all assessment data can or should be assumed to follow normal distribution, but in this case, they do. The SOL scores do, which allows me to use parametric statistical tools. This error bar chart illustrates the marginal means for each PLD, that's represented by a bullet, and the upper and lower bounds represented by those whiskers. They're grouped by grade level across all models. And as you can see, students in math who received PL-2 consistently underscored students who received PL-1, who in turn consistently underscored students who received, I'm still an administrator, who received PL+1 across all grade levels. The one outlier was PL+2 for grade 5, which actually had a lower mean than +1. By examining these error bar charts statistically, we see consistently that the lower the PL, the lower the SL score, or the SOL score, and vice versa. This is probably unsurprising to educators, but now we can say conclusively, statistically, that that is true. For mathematics, with that one outlier, math PLDs are predictive of math SOL scores across all of the models. In reading scores, there's none of that exception for +2. Here we see a very consistent representation of performance level descriptors accurately predicting SOL score. Therefore, reading PLDs are predictive of reading SOL scores across all models. This further verifies that PLDs are consistent effective regardless of model, which reinforces the premise of the taxonomy. The science data further confirms our expectations. PLDs are predictive of SOL scores, so we can draw the same reinforcing conclusion about science as we did for reading and math. Now here comes the real test. Here we are comparing the models to each other. Now I'm going to visualize this in a couple of different ways, so if this kind of looks jumbled, hang with me for just a second. I have another visualization coming up. Taking all of the PLDs into account, comparing models to each other. Given that PLDs are equally predictive and SOL scores are parametrically distributed, we would expect to see similar scores from model to model. For mathematics, this error bar chart displays the means and the upper and lower bounds as before, but shown by model for each grade level. You can see those three represented models at the bottom across all 31,091 students. Now, while this display is statistically accurate, as I said, I think it's meaningful to visualize this in another way. On the left, the data is visualized on the same 380 to 470 point scale as the output was on the last screen. And I made these colorful bars to kind of make them easier to see. The difference between the scores might look relatively wide here on the left, but look on the right. If we visualize that same data on the full 0 to 600 point range of possible SOL scores, the difference is a lot less pronounced, and I think this is an effective illustration of the need to consider effect size. The range between means is actually much smaller than it appears on that first statistics chart that was zoomed in to show as much detail as possible. The effect size is not actually practically that significant. For mathematics, the low p-value describes there's a low probability that the data is incompatible with the model. That is, that the test's model is likely correct and that there is a relationship. But now we look at the more critical factor, Cohen's d, which tells us the effect size. In each case, d is small. For two of the pairwise comparisons, the effect is what Ferguson described as minimally practically significant. Remember, big significance in Ferguson is like 2 something. While the last pairwise comparison has no practical significance, that d is so low at 0.09, the other ones are described as minimally significant because they're not that much higher than that 0.41 lower bound. Therefore, the difference in the ability of class 2 and 3M models to predict SOL score has little practical significance, just like the difference between classes 2 and 4E. And comparing class 3M to 4E, there is no practically significant difference. Therefore, there is no real practical difference between SBRC classes in their accurate prediction of SOL outcomes. This is a pattern that we're going to see consistently across subjects, and for my statisticians and methodologists here, I'm displaying the actual data. Here we see the same test run for reading. Again, while the p-value is very low for each comparison, we look at the Cohen's d for effect size, and again, we find little to no practically significant difference between the three classes for reading, just as we did for math. Here's science visualized in the really small range between 380 and 440 points. While the relationship is again statistically significant, the d values are very low, meaning that the three classes are again practically equally predictive of science SOL score. For students in Virginia in grades 3, 4, and 5, PLD codes are practically effective predictors of SOL scores in each subject, with the minor exception of the PL+2 PLD for grade 5 math. For the classes studied, all three are practically equally predictive of SOL scores for all grade levels and subjects. They are basically the same. Now, while Class 2 students generally outperformed other students, and Class 4E students generally underperformed, the differences aren't practically significant, but also they can't be causally attributed to SBRC class alone, given the small effect size and the number of potentially confounding variables, like differences in pedagogy between the schools. So, findings. To answer research question 1, this study investigated the extent to which SOL test scores are related to PLD codes and grade levels, and found that PLD scores are practically effective predictors of SOL scores at all grade levels and for all subjects. To answer research question 2, this study investigated to what extent SBRC class predicted SOL test scores, and found that SBRC classes are practically equal predictors of SOL scores at all grade levels and for all subjects. This means, in toto, that we can now answer the research questions for the dissertation themselves. Is there a relationship between SBRC class and SOL score? No, there is no practically significant difference between SBRC models. Each SBRC model was practically equally predictive. Another way to think of this, changing a student's report card model from Class 2 to Class 3M would be very unlikely to change that student's SOL score. SBRC model as a predictor of variable appears to have no real impact on the SOL outcome variable. Do different SBRC models offer different levels of predictability? No, there is no practically significant difference. They are practically the same in terms of their predictability. The regression data doesn't show that one model is practically different than another in its ability to predict SOL scores. What does this mean? We move on to the most important research question 3. Are certain models preferable? Now we have to think all the way back to the beginning of this presentation. We must consider everything we've spoken about today, not just the statistics, but that earlier theoretical framework. Are certain SBRC models preferable? Yes. While they're practically equally predictive of skill mastery, that research that shows us that ranking, classifying, and judging students is harmful to them must now hold sway over policy. This suggests that lower t-values are desirable in SBRC models, and therefore lower classes of SBRC model in Reeves' taxonomy are preferable. We can now make recommendations based on this new knowledge. I've identified 3 key areas of recommendation for praxis, as well as several recommendations for future research as we wrap up. Cohn and Miller and others show us that ranking, classifying, and judging children is harmful to them. It's what Vidal in 1992 called ghettoization, the forcible uprooting of a child from their authentic reality and forcing them into a preconceived judgment category. Since there's no practical predictability difference between SBRC classes, we should eliminate as many PLDs as we can. This seems to suggest that lower t-value SBRC models are preferable when it comes to psychosocial health, though specific confirmatory research on this is warranted. While students can and should continue to use proved effective diagnostic instruments to thoroughly understand their students, the reporting classifications and labels should be avoided. Within the context of standards-based practices, under no circumstances should PLDs be paired with numbers or letter grades. They are incompatible, inequivalent, and should be avoided. And I believe that the thorough systematic literature review I did demonstrates that that has already been found to be true. Finally, high-quality, individualized narrative feedback that includes prescriptions for improvement is absolutely essential to any meaningful grading program. Employing Dweck's research on growth mindset, it's helpful to shift our concept of grading away from thinking of meets and does not meet as describing the student or even describing student performance, Just as understanding a child requires a constellation of data, so to teach a child requires a community of educators. I think we should think of it as whether the team of professionals has done everything it can to meet the needs of the child, or whether that team has yet to do so. Couching the whole enterprise of assessment in growth mindset helps to disarm and discard ranking, labeling, sorting, and judging children, and instead helps teachers focus on meeting every child's every need. Additionally, because standards-based PLDs have been shown in this study to be consistently accurately predictive of student performance, I think we can and should consider replacing standardized testing entirely with effective standards-based assessment. Since research tells us that there are numerous problems with standardized tests and that the way that they impact students, again, especially girls and people of color, it is appropriate to eliminate those tests entirely and to replace them with standards-based grading. Again, I understand that this requires future confirmatory study. To effectively educate a community about standards-based practices, and let's be honest, if we were to try to implement everything I'm recommending, we're going to have to talk to our communities. School community relations personnel should collaborate directly with planning and assessment personnel to robustly prepare a program of clear, concise communication. They must avoid the historic deficit model. That's an information theory that says that the reason the public may not understand something or that it chooses the politics it does is because people just don't have enough information. We've debunked that. Consequently, many experts don't consider that facts may be contrary to commonly held beliefs, even if those beliefs are disprovable. Sound familiar? Think back to the theoretical framework of this study and recall that scholars believe that human experiences exist in a social context. Consequently, a well-researched alternative to the deficit model is what's known as the contextual model, which seeks authentic language to speak directly to the lived experiences of humans in a society and help them truly understand concepts. Now, this doesn't mean talking down to people, but rather explaining things in an accessible and understandable context. It's not enough to bombard the public with facts. Real communication takes relationships, and schools have to avoid the pitfalls that have plagued the CDC and climate scientists as two examples, and they need to actively seek to understand, listen to, and speak with, not over, their constituents. Confirmatory studies, as I said, are warranted to replicate this dissertation both within and outside of Virginia. Data that becomes available after this defense, as one did, may prove appealing to immediately follow up with the same methodology. And then different methodology can and should be considered to further test the conclusions therein. I think two key follow-up areas are warranted, and this ties together the last open bow from the beginning. Firstly, as I said, I was disappointed because of the unavailability of sex and ethnicity data in this study. It's essential that we investigate those areas to ensure that if particular SBRC models are better for historically underserved and marginalized populations, or if certain models show certain preferences that are even worse for example, white students over students of color, that's given serious consideration. That that equity data around race and ethnicity and sex has to be more thoroughly investigated. And I'm disappointed I didn't get that data, but I'd like to do a follow-up. Secondly, it is worth specifically testing students' perceptions of various SBRC models and their lived experiences. We should go and ask the kids, as well as look at health and student performance data using existing or research-based instruments, so we can evaluate if actively moving students to SBRC models with those lesser t-values that I recommend does in fact have the expected improving effects that I suggest may occur.